Good afternoon. We are the Jpf-Logic team, and we will present our framework Jpf-Logic. We will start with the problem Jpf-Logic addresses. Next, we will discuss our solution and finish with a demo of Jpf-Logic. As Cyril already mentioned in this tutorial, the model checker Java Pathfinder, represented by JPF core, can check for properties such as deadlocks, data races, and uncaught exceptions. JPF's extension Jpf-Numeric can detect overflows and underflows. The extension Jpf-LTL can check for properties expressed in linear temporal logic. The extensions Jpf-Numeric and Jpf-LTL are more than a decade old and are either not available anymore or incompatible with the current version of JPF. Our contribution, Jpf-Logic, enables JPF to verify properties expressed in temporal logics. Now let us introduce two such temporal logics. Linear temporal logic, abbreviated to LTL, was introduced by Amir Panili in 1977. In his paper entitled The Temporal Logic of Programs, which was presented at the 18th Annual Symposium on Foundations of Computer Science, he presented LTL. Panili received the Turing Award in 1996 for introducing temporal logic into computing science and for outstanding contributions to program and system verification. The computation tree logic, also known as CTL, was introduced by Edmund Clark and Alan Emerson in 1981. Their paper, entitled Design and Synthesis of Synchronization Skeletons Using Branching Time Temporal Logic, was presented at the workshop named Logic of Programs. In this paper, they not only presented CTL, but also introduced model checking. For the latter, Clark and Emerson received the Turing Award in 2007. Next, we will provide several examples of properties that can be expressed in LTL and CTL.
The class of so-called safety properties can be expressed in temporal logics. As Leslie Lamport, another Turing Award winner, described in his 1977 paper, which is entitled Proving the Correctness of Multiprocesses Programs. A safety property captures that something bad will not happen. In CTL, a safety property is expressed by a formula of this form, consisting of a universal quantifier symbol followed by a box followed by a negative symbol. It expresses that in each reachable state of the system, something is not the case. For example, we can express that the balance of a bank account is never negative in CTL. Another class of properties known as liveliness properties were characterized by Lamport as something good must happen. In CTL, a liveliness property is expressed by a formula of this form, consisting of a universal quantifier symbol followed by a diamond. It expresses that in each execution of the system, at some point in that execution, something is not the case. For example, we can express that the main method always terminates in CTL. There are, however, some challenges when model checking systems with large state spaces. In these cases, JPF often runs out of memory or takes too much time to complete its model checking effort. When this happens, the state space of the system is only partially explored. We can model such a partially explored state space as a partial transition system. Such a system consists of states depicted by the circles and squares and transitions between states depicted by the arrows. We distinguish between two types of states: states that have been fully explored by Java Pathfinder, which are denoted as circles, and states that have been only partially explored by Java Pathfinder, which are denoted as squares. These partially explored states may have additional outgoing transitions that Java Pathfinder has not yet traversed. We indicate the initial state by this incoming arrow. The states are labeled with so-called atomic proposition. This atomic proposition can capture properties such as the balance of the bank account is negative and the main method returns. In the examples, we represent the atomic proposition by colors. In this example, two states satisfy the atomic proposition, green, and one state satisfies the atomic proposition, purple.
To reason about partial transition systems, we consider all possible ways in which it can be completed to an ordinary transition system by adding states and transitions. For example, consider the partial transition system that we discussed earlier. Here are three of its completions. In the leftmost completion, we add a single transition. The completion in the middle contains one extra state and three additional transitions. In the leftmost completion, we add two states and three transitions. Note there are infinitely many other completions of this partial transition system. Given a partial transition system modeling a partially explored system and a property expressed in temporal logic, we may ask ourselves, when are we sure that the partial transition system satisfies the formula? If no matter how we complete the partial transition system, the formula is satisfied in that completion, then we can conclude that the formula holds in the partial transition system. For example, this partial transition system satisfies this formula. The formula expresses that there exists an execution path that will contain a purple state. No matter how we complete the partial transition system, this brown path will be part of the completion and it contains a purple state. Let us look at another example. We consider the same partial transition system. This time, the formula specifies that there exists an execution path with only green states. The brown path is such a path. As in the previous example, no matter how we complete the partial transition system, this brown path will be part of the completion, and therefore, the partial transition system satisfies the formula. Given a partial transition system modeling a partially explored system and a property expressed in a temporal logic, we may also ask ourselves, when are we sure that the partial transition system does not satisfy the formula? If no matter how we complete the partial transition system, the formula is not satisfied in that completion, then we can conclude that the formula does not hold in the partial transition system. For example, this partial transition system satisfies this formula. The formula expresses that each execution path contains a purple state. No matter how we complete the partial transition system, this brown path will be part of the completion, and it does not contain a purple state. We have seen when a partial transition system satisfies and does not satisfy a formula. In the former case, all its completions satisfy the formula, and in the latter case, all its completions do not satisfy the formula. But what if some completions satisfy the formula and other completions do not? The best that we can say in that case is maybe. For example, this partial transition system may satisfy this formula. The formula expresses that all states reachable from the initial state are green or purple. This is a completion that satisfies the formula since all states are green or purple. And this one does not satisfy the formula since a brown state can be reached from the initial state. As we have just seen, to solve the model checking problem for partial transition systems, it suffices to compute the set of states of the partial transition system in which the formula must hold, the formula cannot hold, and the formula may hold. A very similar problem was tackled by Glenn Burns and Patrice Godefroy more than 2 decades ago. This is a high-level overview of our framework Jpf-Logic. As input, represented by the purple ovals, it takes the bytecode of a Java application and a formula. Furthermore, one can configure Jpf-Logic. In the configuration file, one can set JPF properties such as target and class path, as well as which logic to use and where the file with the formula can be found. As output, represented by the green oval, our Jpf-Logic provides the result. The formula must hold, the formula may hold, or the formula does not hold. The brown boxes are the components that we developed for our tool. The white boxes are components developed by others that we use in our framework. We developed a compiler that generates an abstract syntax tree for our formula. The formula and configuration file are used by our converter to generate a properties file for JPF. We also have developed a listener for JPF that generates a partial transition system modeling the Java code. The abstract syntax tree representing the formula and the partial transition system modeling the Java code are provided to our model checker. This model checker verifies whether the partial transition system satisfies the formula.
To apply our framework to a new temporal logic, you need to implement a parser for the logic. Develop a hierarchy of classes that represent the abstract syntax of the logic, and implement a model checking algorithm for the logic. Let us have a closer look at these three components. The parser takes as input a string representation of a formula and produces an object in Java that captures the formula. We have implemented a parser for both LTL and CTL, using the parser generator Antler. The abstract syntax trees for the logic are captured by a hierarchy of Java classes. Here we show part of the hierarchy that represents the abstract syntax of CTL. Similarly, we have developed such a hierarchy for LTL as well. The model checker takes as input the partial transition system, represented by the system class, as well as formula, represented by the formula class. As output, the model checker provides a result object, which contains a set of states of the partial transition system in which the formula must hold, and also the set of states in which the formula may hold. To show Jpf-Logic in action, we consider a simple example consisting of 4 classes. The account class that represents a bank account, which has a balance field and deposit and withdrawal methods. The threads deposit and withdraw, deposit to and withdraw from the account. The check threads check that the balance of the account is not negative.
To check that the balance of the account is always non-negative, we introduce this file. The alias negative captures that the Boolean static field named negative of the class check of the package Jpf-Logic examples is true. The CTL formula for all box not negative specifies that the balance of the account is always non-negative. We also introduce this configuration file. We specify where the file containing the formula can be found, as well as which parser and model checkers to use. Let's run Jpf-Logic. The formula does not hold since the withdrawal method of the account class is not synchronized. The alias return captures the main method of the main class of the package Jpf-Logic examples returns. The CTL formula for all diamond return specifies that the main method always returns. Jpf-Logic confirms that the formula holds. We can limit the amount of time that JPF runs by setting these properties. As a result, JPF only partially explores the state space. Even for a partially explored state space, Jpf-Logic can still confirm that the balance of the account is not always non-negative. Jpf-Logic cannot determine whether the main method always terminates when the state space is not fully explored. Even when the state space is only partially explored, Jpf-Logic can verify some formulas, such as that there exists an execution in which eventually the method withdraw is invoked.